Alright, friends and neighbors, today we are talking about capacitance, and there are these little things called capacitors. You see one there. There's some other kinds that they can look a little bit different than that, but they all do the same thing. They store charge. They do that very simply. Inside this can that you have right here is a two little plates of metal. Alright, so if you had a piece of metal here and a piece of metal here, and you ran that to a battery like so, long positive pole, negative pole. A lot of times we put a switch on this thing just so that we can turn it on and off. Put a resistor in there to kind of moderate the current. When I close the switch, electrons are going to leave the negative terminal of the battery, and they're going to stack up over here on this side of the capacitor. Okay, there's all those electrons that came from over here, the negative terminal, marched around. They're attracted to the positive terminal. Unfortunately, they can't get there. There's this gap in the middle. There's some space that keeps them from making it all the way around to the positive terminal of the battery. And you can put different stuff in there. We'll say a little bit about that. If it's a better insulator that keeps them from jumping across there, then it makes a better capacitor. Anyway, meanwhile, all the free electrons here, the ones that can go somewhere, are going to pull over here to the positive terminal of the battery. When the electrons leave this side, that's going to make a net positive charge over here, like that. And once I get this thing charged up, after I close the switch, after the current flows through the resistor, and the charge stacks up here and the positive charge on the other side, why then I could take the rest of the circuit away. I could remove, and my removing instrument here is not terribly handy today, but I think you get the idea that that charge is stuck there, right? And that charge is stored on the capacitor. To me, you know, maybe this is a little bit simplistic, I don't know. But every time I drive past a water tower in the city of Columbia or wherever I am, the purpose of a water tower is to store water, right? And they're going to pump some water up into this thing, and then the water is there for when I need it. See if I can, oh man, now we got a blue water tower. Wanted a red water tower. There we go. And we'll have some blue water maybe. Okay, I put the water in here, right? And it stores that water, and then there's a little valve down here, and I can either open that valve and let it out, or I can put more water in. It's the same thing with the capacitor here. I can put charge into this capacitor and store it, or I can let it back out and use it. Alright, so it works a lot the same way. Alright, I am going to try to turn the page here. There we go. Got a couple formulas that we want to be able to think about. You see the picture that we just drew there. Again, there's usually a switch and a resistor to do that. You wouldn't have to have one, but you know, they kind of make it easier to time how long this thing has been closed for. Let me just show you these formulas here. C is what we call the capacitance, and the capacitance is a measure of how much charge it can store whenever you put a certain battery on it. So down here is your battery V, and I'm going to put a certain amount Q on here. You always have the negative amount here and the positive amount there. So maybe this is, you know, minus, I don't know, 2 millicoulombs here, and this would be plus 2 millicoulombs, just making up that number. And that's what happens whenever I put a 12-volt battery on this thing. Well, I can come over here and say, how much charge did I store? And the answer is I've got 2 millicoulombs, and I used a 12-volt battery, and I could get busy with my calculator, which I didn't pull up. Let's see if I can find it here. I got to go to the screen. I apologize. All right. And I could do that little division there. I could say 2 millicoulombs. I'm going to put 0.002. Get rid of that milli there. And divide that by 12. And I get a number here, 1.66 times 10 to the negative 4. Okay, that would be the capacitance of that. When I put a 12-volt battery, if it stores 2 millicoulombs, then we have measured how good of a capacitor this is. And the unit here is farads. A farad is a lot of capacitance. So usually these will be 10 to the negative 4, 10 to the negative 6, and we could call this 16.7 millifarads. That would be fine. That's not an unusual size capacitor there. So that would be the thing. You can see that the symbol for a capacitor is just simply two straight lines. Remember that a battery was a long line and a straight line. Well, these are the same length because it's like two pieces of metal, and I put negative charge on one and positive charge on the other. So that's an apt symbol there. And you know, I can store up some charge. There are some other kinds of capacitors. All of these down here are capacitors. You have these metal cylinder ones. Those are called electrolytic capacitors. There's an electrolyte in there between the two plates that keeps them insulated and everything. There may be some other kind of material in there. If you just have vacuum, we talk about the dielectric constant, and the symbol for that is K. You can see that over here. Vacuum has a dielectric constant of 1. If you put glass in there, that's a better insulator. So now I've kind of made this region in here stronger, less resistant to electrons jumping from here over to where they want to be but can't get to. Glass would be a better insulator. So somewhere between 5 and 10, depending on the glass. Mica is 3 to 6. Mylar is pretty good, 3.1. That's like a little plastic sheet. So, you know, those are the electrolytic capacitors. I also have these little ceramic capacitors here. Basically, it's just a round plate with a wire welded on, soldered on, and a second circular disc with a wire soldered on. You can almost even see the wire sticking out there. And then they put some kind of dielectric between them, and then dip the whole thing in ceramic or plastic or something insulating to hold it in there. So all of those guys look like little chiclets, or you know, some kind of little piece of gum or something. Those are capacitors. This one's kind of interesting here. This is a variable capacitor, and you can see there's plates right here and other plates right there, and you can actually turn the knob up here at the top and move those plates in and out. And as you move the plates in and out, now they have more plate area. If I made these plates bigger, then I could put more charge on there with the same battery. So that would change my capacitance of this thing. Here's the formula that we're interested in. The capacitance is equal to K, the dielectric constant, times epsilon naught. That is a constant. 8.85 times 10 to the negative 12 farads per meter. It's going to fix the size. It's going to fix the units. So we always put that constant in there. And then A would be the area of the plates. So you could design a capacitor to do whatever you wanted to. Let's say we cut a piece of aluminum foil that was, I don't know, 2 centimeters by 3 centimeters. Something like that. It wouldn't be very hard to get the area of that. We could solder on a piece of wire that touches there, and then I'd need a second one like that. But to calculate the areas, you know, if it's a rectangle, that's pretty easy. Length times width. Probably want to go to meters here. So 0.02 meters times 0.03 meters. And that would be 0.0006 square meters, like that. And I'd put that in for the area right there. If you have more area, you have more capacitance. These electrons don't like each other. They repel each other. So if they have more room, then you can put more of them on there before they start to fight back. okay, before they start to repel and to stop this current coming from the battery. Lastly, down here, you've got D. D is the distance, the thickness of this thing right there. The farther apart you put the plates, it actually lowers the capacity, the capacitance of this thing. If I divide by a bigger number, I get a smaller answer. When I bring the plates up close to each other, then there's that really strong attraction here between the negative charges and the positive charges, and that pulls more electrons in, so I would store more charge, more Q, with the same battery there, so my capacitance would go up with a smaller distance between them. But then I need a stronger dielectric constant here to keep the charge from jumping across too. All right, so capacitors are pretty interesting. You can do a lot of neat stuff with capacitors. You can smooth out real bumpy electrical signals. You can set up oscillations. You can do all kind of stuff with capacitors and resistors and stuff. It's just one more tool in the game here. Okay. I have a way to add capacitors here. Two ways actually. Same as resistors, except they don't add the same. Let's take a look here. Here's our friend Mr. Electron again. He's coming along from the battery, and all of a sudden he sees three capacitors that are in parallel. And you can tell they're in parallel because here's one, and then right next to it is the next one, and the third one. They're all in parallel there, and that's just like making a big capacitor, right? That increases the cross-sectional area of the plate. That means I can put more charge on there. And my capacitance, the total capacitance of adding C1 and C2 and C3 is really easy. I just add them up. If this is, I don't know, 12 microfarads, and this is 20 microfarads, and down here I've got 30 microfarads, then it wouldn't be real hard to come up with 62 total. Whoops, forgot to hit shift there. You ever do that when you're writing? And I would just add those like that, and I'd get 62 microfarads. Okay, so I can make capacitors bigger just by putting one in parallel to it, or get a bigger total capacitance. By the same token, I could also put these guys in series. We did resistors in series, and you remember that we added resistors in series just like we just added the capacitors. But we don't do that here. They work backwards from each other. Here I got to go through this rigmarole. I got to do the flippy thing like we did for resistors in parallel. Okay, so they work backwards. If you see resistors in series, you just want to add them up. If you see resistors in parallel, then you got to do the 1 over R equals 1 over R1 plus 1 over R2 like that. Capacitors work the other way. If they're in parallel, add them up. And if they're in series, then you got to do the flippy thing. And you, of course, remember that there is a trick to that. You could either write it all out, get common denominators, and do all that, but why would you want to do that? You can come here on your calculator, and if I use those same ones we just had, if I can remember them here, I think we had 12 microfarads and 20 and 30 microfarads from that last problem. It added up to 62 before. It's not going to add up to 62 this time. What I got to do is say 12 inverse plus 20 inverse plus 30 inverse equals, hit your inverse one more time, and I've got a total of 6 microfarads there. So for this way of putting it up, C total equals 6 microfarads. Now notice that on the calculator I left off microfarads and then I put it back on. That's fine to do as long as they're all the same unit. If you had millifarads and microfarads, I'd get them all to 1 unit, maybe even farads, and then figure out what you want to do with it. All right, but here, since they're all the same prefix microfarads, then it's okay to kind of leave that out of the calculator work and come back and put it on at the end. You could put it on too if you wanted. You could go 0.000012. There would be 12 microfarads inverse, you know, but why, right? Okay, so just flip them around. They work the opposite way that resistors work. We've said that capacitors store charge, and of course charge is a measure of energy. And so here's a quick way to find out how much energy is there. And remember that energy comes back to work. How much work would that accomplish? So maybe you want to think about it as energy, or maybe you want to think about it as work. But they're kind of the two sides of the same coin right there. I can either take 1/2 Q times V, or I could take 1/2 C times V squared, or I could take 1/2 Q squared times C. Now remember, we did a similar thing with this with power. Over here I'm going to put that little formula about capacitors, C equals Q over V. And here's this first one. This is kind of the stock definition of it right here. 1/2 Q equals 1/2 QV, like that. Well, if I were to solve this thing for Q, then that would be CV. So if I take that CV and plug it in for Q, then you could see that I would have 1/2 Q, which is now CV, times V, and that's going to be 1/2 CV squared, the second way to do it. All right. Alternatively, I could have taken this expression that explains how capacitance, charge, and voltage all works together. I could have solved it for V. Do the flippy thing here. V equals Q over C. Take that guy and put it in right here, and I'll get this last version here. Let's see what we get. 1/2 QV. I'm replacing V with Q over C. And you can see that that pretty painlessly turns into 1/2 Q squared over C, like that. All right, so any of those that you need. Basically, if they give you capacitance and voltage, this would be the easiest way to do it. If they give you capacitance and charge, or charge and voltage, you just pick the one that you need. You could always go back, you know, to that definition right here, you know, because this is kind of the central rule of the thing. And if they give you two, you could find the third one and then use any version you want. But here they all are, and you can pick the one that you want to use. All right. Capacitors charge up. It's not like when you close the switch that bam, it's full. It's just like the water tower again. It takes a little while to pump the water into the water tower. And so right here are some formulas that kind of show how that happens, the rate at which it happens, how long it's going to take to fill to a certain percentage, all that. Let's walk through this real quick. Right here I have the current I is going to be equal to the change in charge over the change in time, and that's going to be equal to the voltage minus Q over C. If you go back to your thing here, C equals Q over V, so you can see that V is going to be equal to Q over C. So they've kind of made this little substitution here. As that voltage changes, and I divide by the resistance, you know, this is pretty much going to go back to V over R equals I, right? This is Ohm's law, V equals IR. Okay, so this is just kind of another version of Ohm's law when there's a capacitor and I'm storing charge in there. As the charge goes up, this number is going to get bigger and bigger and reach the value of capacitance. And when I get that number, then it's going to shut off and the current's going to go to 0. The resistor is going to moderate how fast that happens. All right. This right here is called the time constant. And it shouldn't really be a capital T. It really should be a tau. So that's kind of a typo. Apparently I couldn't find the font. All right. You know about the letter pi, right? The Greek letter pi. Well, if you cut off one of the legs, you get a tau. All right. So that's what should be sitting right there, and I apologize for that. I'm going to replace this one down here too. I guess you could use the big T if you wanted to. But that's kind of a special number. Tau is the time constant. It's the time that it's going to take to fill up to a certain percentage. All right. All you got to do to find that time constant is to multiply the resistor down here. That would be 100 ohms in this picture, times the capacitance, and here that would be 0.001 farad. I've gone ahead and done that here. 100 ohms times 0.001 farad, and you get 1/10 of a second, 0.1 seconds. And that is the time that it's going to take to fill this thing to a certain percentage. The certain percentage is 63%. Okay, and you say, well, that's kind of weird. And yeah, it is. But the graph of this thing, that was supposed to be a nice straight line, x-axis. Oh, man. It's just getting worse by the minute, isn't it? There we go. There's an x and a y axis. When I graph this thing, I'm going to get something that looks like, apparently Control Y doesn't work, so let me draw my x-axis back in there, like this. And the graph of this thing is going to come like this. It's full to capacity, and it kind of approaches like that. It's an exponential growth to a maximum. There's some maximum amount of charge over here like that. So I'll put Q max right there. And this would be how much charge per time is on the thing. When I close this switch down here, there's no charge on the capacitor. And I close the switch, electrons start moving this way, and they build up a little bit of charge, and they keep flowing, and there's more and more and more. Turns out that the electrons rush to get the first seats in the theater, if you will, and then as it starts to fill up, they slow down. The flow of electrons slows down there. So I get what's called an exponential growth to a maximum. And that's kind of a neat graph right there with that thing. The form of that you can see down here. The charge on the plates at any time is equal to Q naught. And really, Q naught's the way you see this written, but it's better, I think, to write Q max. How much charge can I put on those plates? Times 1 minus e to the negative t over tau. That with a tau too. Okay, that is the formula that says at any time t, how much charge Q do I have on there, and it's going to go all the way up to Q max. This 1 minus e to the negative t over tau gives me that curve. Q max tells me what my maximum level is, and the time I'm measuring this way to get up to a thing. Now remember that 63% that we talked about. 63% full would happen about right here. This is 100% full up here. So when it gets to 63%, there's some amount of time, and that amount of time is what we refer to as tau. Okay, it's the time it takes to fill to 63%. You say, well, shoot, what's up with the 63%? Checking this formula right here. If I just put in 1 minus e to the negative 1, look what you get. 1 minus e to the negative 1. There's my 63%. Okay, so that 63% is what you get here when the time is equal to 1 tau, and that's why 63% is the measure. The difficulty with saying, well, how long does it take to reach 100% is because, you know, the graph here is approaching Q max asymptotically. It gets closer and closer, and what you know, if anything about calculus, then you know that technically that happens at infinity. So to say how long does it take to fill to 100%, that's kind of hard to get to. All right, but the 63% is an easy way to say, well, I can find that time, and it's right there in the formula. All right, I'm going to do one of these in a little bit, but that's the idea. If I want this thing to fill up slower, then I could put a bigger resistor here. A bigger resistor would reduce the current, and that means that fewer electrons are coming and filling up this plate. Or I could reduce this resistor, and then that would give me a higher current, and it would fill up faster. So you can kind of treat this thing to, control it, if you will, with that resistor there. Couple formulas that you should remember when you do this. One is V equals IR, and that kind of led to this thing up here at the top. And the other one is our rule on capacitance. C equals Q over V. Notice that we need Q max right there. So to get that, all you got to do is say, well, Q would be equal to C times V. And I could come in here and I could say, well, I got C and I got V. That'll tell me how much charge I can possibly store on this capacitor with a 12-volt battery. Let's see what that number is. Right here I'd have 0.001 farad. That's my C, my capacitance. And then 12 volts right there. And so I need to move that decimal place 3 times, and I get 0.012 coulombs of charge. That's Q max. Okay, you kind of need to do this calculation first so that you can put it right here. 0.012 coulombs is Q max, and you got to know what that is. The second thing you got to do is you got to get tau. And we've already done that right here. So you got to know what those two numbers are before you can do the rest of this thing. But after that, let's say that I close this switch and I want to know how much charge there is after 0.12 seconds. Well, I could come in here and put in my formula. Q equals Q max, and Q max was 0.012. Put in your parenthesis, 1 minus, right there's that E in yellow, so I got to hit the yellow button and then E. And we wanted to say, what was it? What did I say? 0.12, I think. So I got a negative 0.12 seconds over 0.1 seconds right there. T over tau. And that's going to look like this. Remember that I'm a little bit past tau. Tau will be 0.1 and I'm at 0.12. So I'm going to be somewhere north of 63% here. 63% of that number. And, 0.008. Okay. It's not up to 0.012. I guess you could come in here and divide by 0.012 and see what percentage we have filled. About 69%, 70%. Okay, so I'm about 70% full at that time. If you just wanted to know the percentage, then you could leave Q max out or just put a 1, for 100% there, and then just do this part. But that's the way that works. And we'll do one more of those here before this is over with. I want to show you one more thing here. Remember we said that that I can put that charge in the capacitor and then pull it out when I need it. Maybe I need a little bit of electricity for something. Think about the exit signs, the emergency exit signs in a building. They're hooked up to the electrical power. when the power line goes down and the electricity in the building goes off, you want people to be able to see the signs and be able to get out of the building. So you need that light to stay on even though there's no electricity. So I could come in here and make a sign that says exit, and there's a light bulb behind that, right? And when the power is on, well, I could just hook that up to the electricity. I could plug this thing into the wall. However, if I just do that, if the power in the building goes off, then the light bulb goes off, and nobody's going to be able to find their way out of the building. So what I need to do is to have a capacitor in here and hook it up to my power. I need to put a resistor in there to kind of moderate how fast this thing is charging. And I could do like that, and then the electricity, while it's on, would both run the light bulb and charge the capacitor. And when the power goes out, then I no longer have this, but I have all that charge stored up in the capacitor, and it could come out and run the light bulb for a certain amount of time. And we could calculate how long that light would stay on. It's going to depend on this resistor and the resistance of the light bulb and the capacitor here. But you've got Ohm's law, and you've got your capacitance rule. And then you've also got this formula right here that deals with the discharge of your capacitor. And you can see that this is an e to the negative exponent, right? This is an exponential decay function. So I don't know how familiar you are with those, but basically it's going to graph out like that. And that's supposed to come on down here to 0. All right? There's going to be some amount of charge on my capacitor when it starts, and as time goes by, that capacitance is going to run out of the capacitor through the light bulb, and the charge left on the capacitor is going to approach 0, again asymptotically, so it doesn't make sense to say, well, how long does it take it all to run out? So once again, we're looking at that 63%, because that's the that e to the negative exponent there is what's left. Actually, at one time constant tau, I have 63% left, which is to say that it fell 37%. I lost 37%, and again, why 37? Because if you go e to the negative 1, then you get 37%. All right, so that's what's going on with that. The capacitor can charge up, it can discharge. I've got a blank screen here, so we'll do one more of these, but it's really not that hard. You just punch it in the calculator just like it looks. And so let's see what happens here. I'm going to make a circuit that has a capacitor of, let's go big here, 0.3 farads. And I'm going to put in a resistor of 300 ohms. Okay? So let's go ahead and build that. Here's my resistor. Here's my capacitor. I need to hook this up to a battery to supply the voltage to charge up that capacitor. And I'm going to say that's a 9-volt battery. So here comes my wire and my positive terminal, negative terminal of the battery. And I'm going to put in a switch just to make it easier to talk about when we close the circuit and make it go right there. So that would be a circuit. All right, this is the capacitance, or the capacitor. This is the resistor, and this is the battery over here. So remember I said there were a couple things that you wanted to calculate before you got started. One was the time constant. And the time constant was simply R times C. So I need to go 300 ohms times 0.3 farads. And I think that's going to be, I don't know, 90, is that right? 300 times 0.3, yeah, about 90 seconds. Okay. It's going to take 90 seconds to reach 63% of Qmax. Well, how much is Qmax? Well, that's the second thing I got to find out. And to do that, what I want to do is to remember that C equals Q over V. This is how much capacitance I have. I know that. That's 0.3 farads. I know what battery I put on there, 9 volts. So I want to solve this thing for Q, and even if the resistor and the switch and all that weren't there, this would tell me how much charge I can possibly put on that capacitor with that battery. So I come in here and I go, I got 0.3 farads, multiplying that by 9 volts, and I think that's 2.7, is it not? 0.3 times 9, 2.7, okay? And that's coulombs of charge that we just found right there. So I got to get this number, and I got to get this number right here, because those are the two numbers that I need for my formula, like in the rest of the stuff that we're going to do. When I close the switch and this thing is charging, I'm expecting it to do that exponential growth to a maximum. I've got the maximum, and that's this number right here. There's no way it's going to let me write that in there. Put it way out there. Okay? And it's also going, and the speed, the rate that it does that at, depends on the time constant, tau. And of course I got that. So I got those two numbers, and let's say the question says find Q after, it takes 90 seconds to get to 63%, so we can pick pretty much anything you want here. T equals, I could put 4 seconds, and I'd have a very small amount of charge, or 40 seconds, and I still wouldn't be up to 63%. It might be around 40, 50% maybe. Remember, it likes to fill up fast, and then those last seats take longer to sell. But I don't know, let's go 400 seconds here. Okay, 400 seconds gets me out way past the time constant. If I have 400 seconds and I'm cutting that up into 90-second chunks of time constant, that's 4.4 tau. .44 times the time constant right there. So when I write this formula, Q at any time is equal to Q max times 1 minus e to the negative t over tau. You see how that t over tau is kind of this number right there, that 4.44? Okay? It's saying how many time constants are you going out there. Here's 1, here's 2. Oh man. I don't know if I can get in there or not. Let's start way up here. Here's the second time constant, and the third time constant, and the fourth time constant. And we're out here somewhere. Okay? So we're going to be getting really close to maximum charge on this thing. Let's just run the numbers and see what we get here. Qmax is 2.7 coulombs. And I go 1 minus e to the negative t. T was 400 seconds. The time constant tau right there was 90 seconds. Okay, so again, that's going to give me the 4.44, and I could just put that if I knew that, but you just grab your calculator, put it in just like it shows. I got 2.7 parenthesis 1 minus E, second natural log button, like that. Don't forget the negative. 400 divided by 90, and I'm at 2.67 coulombs. Okay, and like we said, not quite there, but we're getting close, right? We've reached, you know, up there, and you can put any other time in there that you like, but that would be the charging of that thing, and it would get all the way up to that point. I'm going to erase this, although it doesn't really like to erase, does it? Try to make a little bit of room. We'll discharge it, just so you can see that. Oh, there we go. Good. All right, so when I discharge this thing, the only real difference is I've got a different number. I mean, a different formula. Discharge, and maybe we charged it up 2.67 coulombs. So I'm going to put Q naught, Q initial, equals 2.67. I charge it up for 400 seconds. I take the battery away. Maybe I wait 3 weeks, or maybe I go ahead and start using that charge right away. Whatever, it doesn't matter. It will store it on there, theoretically, as long as you want. Here in the south, where it's super humid, you've got water vapor in the air. It's going to bump up against the wire, and some charge will be transferred to the moisture in the air. Okay, so you will kind of lose charge over time if you put it, we don't need to go into that, but let's say I've got 2.67. I charge it up, and then I take the battery out, and I don't have the switch open, right? I'm sorry, I don't have the switch closed. So, you know, we've loaded this thing up. I got a whole bunch of negative charge. This plate, I got a whole bunch of positive charge on there. The switch is open, so it can't go anywhere. It's just stuck on there. And whenever I want to discharge the thing, then I use the other formula. The Q at any time would be equal to the initial charge times e to the negative t over tau. So I'd have to know this other time t here. Let's say discharge, we want to find Q after 14 seconds. How much charge is left on that thing? So I'd come in here and say, well, I started with 2.67 coulombs, and then I got to multiply that by e to the negative 14 seconds over tau. And remember that we haven't changed the resistor in the capacitance. We could change the resistor, you know, if you want to, but let's leave it the same here. My tau was 90 seconds, so I got to put that in right here. And I push some buttons, and I get a number on that, 2.67 E, second log, negative 14 divided by 90. And I'm down to 2.28 or 2.29 coulombs. That's what's still left on the capacitor, and I could use that another day. Okay. So all kind of applications, all kind of uses for these things. A stun gun is a great big capacitor, right? Remember the old disposable cameras? I had a kid, he just loved going to the drugstore and saying, hey, do you have any old disposable cameras? And they'd say, yeah, here's a bag full of them, because we're sick of them. And, you know, after they took the film out to develop it, they just throw them away. He'd take them home and use the battery, charge up the capacitor, and run around and shock his sister or something, you know. But that had a capacitor in it that you could discharge very quickly when you touch it to your sister's arm. So, anyway, I hope that makes sense. If not, in recitation, ask all the questions you like. And basically, you need to know how to add these things in series and parallel. You need to know how to find the how much charge there is at after a certain amount of time, whether you're charging or discharging. The design of the capacitor. Remember, we We had those other formulas there. One of them's already on there, C equals Q over V. That's a good one to have up your sleeve. But then if you want to build yourself a capacitor, if you're designing this thing, how much area do you have, and the distance between the plates, and then you have that constant epsilon naught. Wouldn't hurt to put the value of that down, 8.85 times 10 to the negative, oh mercy, 12 I believe. Where'd it go? Yeah, 8.85 times 10 to the negative 12 farads per meter right there. All right, so you know, that wouldn't hurt. Hopefully I'd remember to give you that on the test, but if you had it on your card, then you'd be ready to go. Farads per meter. That's what I said. Yeah. Hard to talk and walk at the same time. But I think that's good enough for capacitors. All right. Have a good day, and best of everything. Thank you.